Good afternoon, everybody. Welcome back. It's been a while, but got some time this nice Saturday afternoon to work on the puck holder project, and so figured I'd stream along. To catch you up to speed, it's been a while since I have streamed, and that's because it's been crazy busy trying to get these things ready to assemble and start delivering to customers. Like lots of things that you don't even think about. One of which, I'll give you an example. You open up an Internet of Things device. Inside the box, there's some sort of instruction card to help people who are unfamiliar with tech get it connected to their Wi Fi. And so you have to build a card that goes in the box. Like, I'm not a graphic designer. This thing took me like, I don't know, I'm embarrassed to say how many hours. A lot of hours. And like a graphic person would probably look at that and make fun of it. But just things like that you have to figure out. How are you going to ship it? We've had to work out box logistics and like, is there the right size box? And do we have the packing material? Like all the things that are not writing firmware or back end stuff, but all things that you have to do when it's just a two-person company. Um, and so at this point, hopefully we'll be able to hire somebody in the future to do some of this stuff. But anyway, we're marching towards launch, which is coming up really fast. October, hockey season starts the second week of October, and I want to be shipping these things out like the first week of October so that people can get them right before the season starts. And so, what are we working on today? Well, as part of this, I think I've got the firmware in a good spot. I've got deploy the fleet in a good spot. I've got the stat feeder backend in a good enough spot. I have backlog items for days on all those things. But what I'm working on right now is the provisioning, or provisioning is such an overloaded term. I'm working on the process of programming them and getting them ready to ship. And so one of the things that I hated, this is the original puck hardware. With the particle P1 module on it. One of the things I just hated about this was how cumbersome it was to program this. Like the P1, you had to like put it into DFU mode to get the two partitions programmed on, and then you had to put it into setup mode to get the bootloader updated. Some of this might be different nowadays. Again, it's been like a year and a half since I've been in this ecosystem, but the process was just garbage, like not production ready at all to program the particle hardware. It was several minutes just to get one thing programmed, and you had to, I wrote a script, like I automated it, and so I still had gotten it down to, it was probably 2 minutes. Like if you got in a groove, probably 2 minutes per device, which, you know, you do the math, like that doesn't scale super well. It'd be nice if it was lower. And so I'm trying to get the process of getting the firmware on down to as quick as possible and as foolproof as possible too. And so I want to cover a couple of things before we get into me working on that. I want to, well, so let's talk about what would we do. Let's clear out this. You've got your Visual Studio Code, you've got your firmware and stuff. When you're developing, what you do is you just plug it into the USB port on your computer. And in my case, I just hit Control Alt T because I've got tasks set up, and I've got this flash and monitor device task, which takes care of flashing everything onto my hardware. And something that I discovered recently, which is really going to save me some time, is I need to change it back so that you can see it. It's tasks. No, it's settings. Right here. This was 921,600 is what I have it set to currently. It was, what is it, 115,200? Oh, 115,200. This is what I had it set to. And this is just a very simple thing that will save you a ton of time, and I'm sad that I didn't discover it until just recently. So this is how I had it set. I'm going to go ahead and plug in one of my devices. And then I'm going to come down into here and do Control Alt T, flash and monitor device. So I'm going to do that, and we'll see how long it takes. I should time this. Dang it. I don't have anything to time it with. Where's my clock? I don't have the second showing. Well, I've got the stream time. So it's been going for about 8 seconds. So 5:10 into the session. So we'll see how long that takes. This will be a guesstimate. You can see it's like 2%, 2%, 2%. Anytime I update the firmware, and just like when you're fast iterating on code changes and stuff, this is what we're dealing with. Like, it takes time to program the firmware onto the physical hardware. And so, goodness, like, it's been a few days since I changed this setting, and I don't even remember how slow this was. This is crazy. What'd I say, 5:10? So we're coming up on 1 minute. Almost there. It's crazy. And so I think this is the default. If you don't specify anything, I think it defaults to 115, 200. All right, and ready to, okay, boom. So about a minute and we'll call it 10 seconds. Oh, and we're in provisioning mode. Yeah, so about a minute and 10 seconds to program. That, I mean, that's just to get the firmware. Well, that's programming the bootloader, the partition table, and the firmware, I believe, all at the same time. But so now let's undo this change and save that. I don't know if this is the max. I think it depends on the chip that you have. And as I was doing some research on this, it really depends on what USB chip you're using to communicate with ESP32. So like some of the dev boards use the, oh shoot, I can't remember. They don't all use the FTDI chip. They use another very common one, but they have max transfer rates. And so I have no idea, and I'll look at this later, but I got to a point where this was fast enough for me. If 921K is the peak for the, because I am using an FTDI 232U, I think, chip. It's an FTDI. It's an official FTDI. And so now let's get out of here, and now let's try it again. Flash monitor device, and I'll start it when we get to 40 seconds. Go. All right, now watch this. It's going to connect 2, 4, 6, 8. Like, you can see it's really kind of jamming. Let's see, that's 10 seconds. We're about halfway through. And are we going to beat 20 seconds? Almost. Okay, 23. 23 seconds. So from a minute and 10 seconds to 23 seconds. That's a huge, huge difference, especially as you're iterating in development, but also on the side of, I've got 500 of these in my office here that I'm assembling. If I get an order, well, I'll get to that. If you need to program a lot of these and it's taking a minute and 10 each, so let's do the math. Let's get out of hexadecimal mode here. Go to decimal. We got 500 puck holders times 70 seconds is that, divided by 60 seconds. That's 35,000 seconds, 583 minutes. That's 9.72 hours. That's insane. Did I do that math right? Somebody check me on that. That's over a full workday just to do the step of programming the firmware onto the device for 500 units. That feels crazy. 500 times 70 seconds is that many seconds. And then if we divide that by 3,600, that gives us the hours. Yeah, 9.72. Okay. Yeah, over 9 hours to program these. And that's assuming, that's not even including the, like, I've got to disconnect it and set it over here or do something with it. So, like, you can see where I'm going with this. Now, as opposed to, where did I get to? 23 seconds, I think I said. Times 500. Divided by 3,600. As opposed to 3 hours, over, about 3.5 hours, with just by changing the baud rate that we program at. And so, that's a huge, huge difference. And so, like I said, I'm embarrassed that it took me so long to figure that out, but hopefully that can save you some time, and hopefully you have a chip, a USB to serial chip that can handle a higher baud rate than 115 too. So anyway, that was something that I discovered last week and is going to be a huge time saver. So, and again, a time saver on the dev side. Also, it's going to be a time saver on what I'm working on right now, which is the programming side. So let's get out of here. Okay, so one of the things that I struggled with when I was shipping pucks, and I did not ship a ton of pucks, but it was a hassle, is, well, let me see it. This is the puck. Let's see that. So what we had to do was we had to program the firmware onto it. We had to assemble it into its case. I then had to, the way that the particle stuff worked, I had to create an entry for it on the particle cloud so it was associated with, like, to keep track of, hey, this person with this email address owns this puck. And this was all a process, and it was like pretty tedious and high stress, like to make sure, like, do I have all the things correct and in the right order? And what got really crazy was on days that I got like 3 or 4 orders of these, I've got them all spread out on the desk. I've got them laid out. One's for the Washington Capitals, one's for the Nashville Predators, one's for the LA Kings, and one's for the, we'll say, another Washington Capital. So 2 Washington Capitals and then the other ones. Well, the way it works currently is I associate those before they go out to the customer so that when the customer gets it connected to their Wi-Fi, they don't have to do anything else. It already knows what team it's tracking and will show stats. Well, that means some amount of association has to happen on the back end before it gets to the customer. That's going to change in the future. The app that they use to connect it to Wi-Fi will also be where they set up their team association, team or player association. And that will help tremendously because then I can just stick raw puck holders that have been programmed with the firmware. I can just throw them in a box and send it to anybody. It doesn't matter. And then the association can happen on the customer side. And so that's a down the road, we'll get there. Right now, I have to make that association ahead of time. And so not only do I have to make sure that I'm associating the correct hardware with the correct team, then I've got them all laid out on my desk, and there is no indication. Again, on the pucks, I at least had the team name. So if I had my order list of like, oh, hey, this person was supposed to get a Capitals and this person was supposed to get a Predators, if those were the only 2, I had the puck to show me like which one goes in which box. With the puck holder, there's nothing. There's nothing on here that tells me this is the Capitals or this is whatever. And so if I've programmed 5 of these to put in boxes, and if I get them mixed up, I'm going to end up sending the Washington Capitals one to the Nashville Predators fan and vice versa. And that I can fix that. Like I'll get a support email saying, hey, what the heck? This isn't showing the right stats. It's not, oh, send it back. I can fix that on the back end. But to avoid that, like I want to avoid that. That's pretty amateur league. So I'm trying to come up with a way to automate as much of this as possible so that I don't even have to think about it. It's just like grab a puck holder, do some things, put it in a box, it's done. And so again, this isn't something that you think a lot about when you're trying to make a product. It's like, oh, how do I make sure that the firmware is good and the back end's good and all the tech works? You don't think about, how do I make sure that the process of getting these things ready to ship out is as efficient and error-free as possible? And so that is what I'm working on. And there's 2 sides. I've decided to break it out into 2 parts. And hopefully by talking through this, I'll either validate that or maybe make some tweaks. But there's 2 things that need to happen before a puck holder can get to a customer. Now, first of all, we've got to assemble it, obviously. But the firmware, the basic firmware needs to get programmed onto the hardware. And so that's things like the partition table, the firmware itself, the OTA initial state partition, as well as the SPIFs storage partition, because I'm storing some stuff in SPIFs on a separate partition. And so those 4 things, regardless of who it's going to or what team it's tracking, need to be programmed onto here. And as part of that, again, for like the SPIF side, even before that, the spiff's image needs to be generated so that it can be programmed on there. There's certain fixed files that I put on that spiff's image that I need to create ahead of time, and so that I can program that onto the device. Now, again, when you're in here in VS Code and you have the IDF extension, you just do what I was just showing you, Control Alt T, flash and monitor device, and it's like, oh, I'll build it if it needs to be built, and then I'll flash everything in the right spot to where it needs to go, and it's ready to go. So you could do that. I could just have VS Code open and then just flash, like run the flash command, disconnect it, put it away, run the flash command, disconnect it, and move on. And that would probably be okay to handle, dozens of orders a day. But it doesn't scale very, very well. And I'm trying to find a balance between there's no need to scale any of this until there's a need to scale it, but I also don't want to be caught flat-footed. And if there's some simple things I can do now to be ready for that in the event that it happens, I think that's good. But again, it's not just about scaling, it's also about error-free. And one of the things that you don't consider, but you might think, well, that's not very error-prone. You just flash it in VS Code. Well, yeah, but what if I'm in the middle of working on a feature branch or something, and I just forget, oh, I'm not on main, I'm on some new thing that I'm working on, and I'm flashing production devices with a dirty dev branch that I'm on. These are things that happen, right? These are simple mistakes that you just, oh shoot, I didn't even think of until it's in a delivery truck somewhere headed to a customer and it's got bad firmware on it. So I'm trying to figure out a way to, again, not just to make it so it's scalable, but also error-free. And so what I would like to have happen is have the programming all separate and be done from a Raspberry Pi. That's how I did the original pucks. I have a Raspberry Pi sitting over here that I would program the pucks with, and it had all the programming stuff on that. I would like to do the same thing, probably with a Docker container is what I'm thinking right now, a Docker image. And that way, all you need to program these things is a Raspberry Pi and my Docker image. There will be an official release Docker image that will have everything that I need for the current release of the firmware to program onto these devices. And so I feel like that's a way to take out some of it's dead simple. You pull the Docker image, you run it, and it programs, and the end. And so that's the direction I'm heading in. And I love the idea of having Raspberry Pi. It doesn't have to be. You could run the Docker image on a laptop or whatever, but the Raspberry Pi makes it, again, a very simple way of, if I need to have 4 people doing this for me, I don't need to buy laptops for them. I can buy $5 Raspberry Pis, set them up, get them a monitor, and off you go, programming these things. And so that's the idea that I'm headed for. So that's the first half of it, is programming just the raw firmware onto the device. The second is that association that I just talked about, where we need to be able to say, oh, hey, Bill from Tennessee, ordered a Nashville Predators one. I need to take this device, associate it with Bill somehow, and tell it to track the Predators. And I think I'm right now I'm separating those two things out, because what I can do is I can assemble all 500 of these in just my spare time. I can do some here and there, do the main programming of the firmware, and then just have them sitting there waiting to be associated for a customer. And so then when I get the order in, all it is a matter of, okay, this puck holder I've got right here, I've got Bill's box right here, I'm going to plug it in, I'm going to do the final step of associating this specific device to Bill and his team, and then I will put it in the box, close the lid, put a shipping label on it, and send it off to Bill in Tennessee. And so that also helps me in separating the work out, right? So if I have an order of, if I need to do 1,000 of these, I can have it completely separate of getting all by that point I'll have it offloaded into the app. But anyway, you can see what I'm going with this. You can split it out. They can be programmed as one step and then put into the next step of the fulfillment area of getting them associated with a customer and a team, and etc. So, all right. I feel like I just explained a lot of what was going on without doing any work here, but I feel like it's important to kind of let you know, the things that I'm thinking about. that you have to do. I mean, you don't have to, but at this point, like I have these ready. I could start assembling them and just like onesie twosie programming them. But I promise you, and I had this with pucks, like you'll make a mistake. I had pucks where I had 3 of them on the desk and I forgot which was which. And the only way out of that was to either like fully connect them to my Wi-Fi to see what stats they show and then figure out whose stats they were, or start over and like wipe them and restart the whole process and like pay closer attention. And so, um, again, trying to figure out the best way to do that, and it'll morph and change over time. But where I'm at right now is, let's talk about the things that have to happen. I covered almost all of it. All those things need to be programmed. One additional step needs to happen in the case of my hardware, which is, you're not going to be able to see it, but I'll put my finger on it. This black chip that my finger is on right there, the lighting is awful right now, is the FTDI chip. Now, the FTDI chip is its own separate, we'll call it a microcontroller for the purpose of what I'm trying to explain, which is it has settings that need to be configured before it will work properly with my hardware. And just for the sake of completeness and helping everybody learn, let's actually show it. Okay. You guys have all seen this before. This is our schematic. If we come into the USB to serial, well, we don't actually even need to come into it. Let's look at it from here and then we'll go into it. So some of the things that are coming out of our USB to serial block in our schematic is this BCD and power enable. We also have the TX and RX, obviously. But the power enable and BCD both feed into the BCD and power enable will come out of the power block and feed into the USB to serial. And that has to do with the behavior of the chip. And so we'll come in here and you can see that we're hooking these up to the CBus 0 and 1 lines. Now, you can configure the FTDI chip to behave a bunch of different ways based on internal registers in the FTDI chip. And you can configure, like I could have made CBus 1 be power enable and CBus 0 be power enable and CBus 1 be battery charge detect. And you could do CBus 2 and CBus 3 for other things. These are all configurable, and unless you choose exactly how the default state is of this FT231 chip, you have to program the FTDI chip before it will interact correctly with the rest of your hardware. Hopefully that makes sense. So we need to program, not only do we need to program the ESP32, we also need to program the FTDI chip. And I did a stream a while back about FTX Prog, which is a program that somebody wrote. It's a C++ project where it will connect to your FTDI chip and you can fiddle with those registers. And so let me show you that. I've got a piece of hardware plugged in. So if you have to run it as sudo. So if I do sudo dev/ftx prog and then run the built ftx prog executable, and I do a dump. You can see it. There's a bunch of stuff that you can change, but it's got all these settings, and the ones that I focus on are I need battery charge detect enabled, which it is not by default. I can show you that here in a second. We'll try. The maximum current supported from USB. And so this is not to get into too much detail, but devices negotiate with the bus on the host machine of like, this is how much current I need. And the OS, the device can limit that. It depends on what quality of a device you have and how well they stick to the standard. But technically, this out of the box, I think is 50. We'll see in a second, hopefully. So where the host will say you don't get any more than 50 milliamps. Well, that's not going to be enough to connect to Wi-Fi with the ESP32. So it'll brown out if it's connected to a computer. So we need that to go up to 500. 500 is the max on the old USB like A ports that are on your that are USB 2, I believe. I think USB 3 has higher limits, but To make it fully backward compatible with all hardware, I have it set to 500. And then I think those are the only two things up here. And then down here are the C-Bus things that we talked about. I need to have C-Bus 0 set to BCD charger, and C-Bus 1 set to power enable. So if those are not configured correctly, my charge circuitry will not work correctly. I did an episode on that where we figured out like how those needed to be be in line with the USB spec in all states of the device, like pre-enumeration, post-enumeration, plugged into a charger, plugged into a laptop. I covered all of that. I'm not going to rehash it here. So, but this is the setting that we need now. And then we can also use, so in this case, I just did a dump. We can use the same FTX prog to program it the way we want to. And so let's grab, I'm going to disconnect this. Stand by. I'm going to go grab a fresh out of the box new hardware and let's take a look at it. Oh, White, can you hear me? This entire box is filled with boards for our puck huddler. Filled with our hardware, which is really exciting. I got boxes everywhere, and I'm really excited to start getting things out of the boxes. Okay, fresh out of the box, we have our hardware here. And so before we even connect a screen or do anything, we can program it. So what I'm going to do, what I normally like to, I'm taking a risk here, just for safety, and this is what I would recommend, do not do what I'm about to do, which is if there is some sort of short on here and you plug it into your laptop, it's possible, however unlikely, that you could fry something or overcurrent and damage the USB or more on your laptop. And so what I normally like to do is plug this into just like a charger, excuse me, just to make sure nothing crazy happens, like no smoke comes out or if it doesn't get super hot. That's just a sanity check. Now, when I move this process over to the programming bench over here on the Raspberry Pi, that's another reason why I like having the Raspberry Pi. I won't do that to keep things speedy. I'll just plug it right in, and if the Raspberry Pi goes poof, it's $5. I'll get another one, right? And so, so anyway, we're gonna roll the dice on this and hope that nothing bad happens. If the stream goes out as soon as I plug this in, it's not gonna be funny, but it's gonna be hilarious later. All right, plugged in. Everything's still running. All right, so now let's run dump with FTX prog and see what we get. All right, so this is the default state of the FTDI chip. C-Bus 0 is transmit enable. C-Bus 1 is the receive LED, transmit LED, and sleep. So these are not the state that we need them to be in to run our firmware. And so we need, like I said, we need to program it. And then let's go up and find the, okay, 90 milliamps out of the box. Again, that's not going to be enough to use the Wi-Fi. You're going to need at least 100, 150 on the low end during transmit, maybe even more. You can get up into the 200s. And then you can also see here, battery charge detect enabled is false. And so those are not the right settings for our hardware. So the first thing we need to do when we're preparing one of these out of the box is we need to program the FTDI chip before we do anything else. So the way we do that, we're going to not continue. Again, the way we do that is with the FTX prog application, the same way we use the dump command. And so when it comes to automation, I'm thinking of two things. I want to program it, and then I want to use the dump command to verify it. When you program it, it kind of verifies and says, like, is this what you want to program? And you say yes, and then it just assumes it does it. It doesn't read it back out and say it worked. And so we have to do that in two separate steps. And so I'm going to stop here and I'm going to unplug this. It's not hot. Okay, so that's a good piece of. There will be failures in these. Like I had this with the puck hardware. I mean, they all look amazing. I especially love, sorry, I'm gonna, like, I don't know how the lighting is. The little 12D logo right there in the bottom in the silk screen. Right here. Oh, there was a good shot of it. I love it. Looks really slick. So where I was on this was what? Oh, okay. Was this right here. And that's all the way at the bottom of the screen. I apologize. But I'm looking for just simple ways. I was originally writing some Node.js and I was like, this is overkill. Why are we doing that? And that is to run the dump and then grep for the things that we're looking for. And if they're there, great. If not, then something has failed. Because I would like to have basically just a bash script that does all of this for me. So it will, like I'll plug it into the Raspberry Pi, I'll run this bash script, and when it's done, the hardware is ready to go to the next step of the process. And so what I was looking at, actually, I'm going to plug this back in. Let's create a new file here so that we can, first of all, you can see it better. What? Stop. New file. We'll call it program device.sh. Okay, and then let's grab what I've been working on. And paste it up here. Now I think I can remove the sudo because we'll launch the whole script as sudo. Okay. And I think what we'll need to do here is chmod add execution rights to it. Yeah. Okay, let's just see if we can run it. Oh, we need to add the bin sh like that, I think. That way we don't have to, we can just do program device. Okay. And great, we got some standard error out here. It's failed to open. That's because I unplugged it. Okay, so let's look at this. Make this a little bigger. So what we're doing is running the FTX prog, which again, I'll build into the image because I'd like to do all this through Docker, and I can show, I'll stream that when I'm working on that. And then I'm just doing the dash dump, and then I'm piping that into grep for now. I'm not sure if this is how it'll stay. And -e is, I think it's extended, so where you can grep for multiple things. And then the C is the count. So if I take out the C and save it. Oh, this didn't, oh, it did exit. Okay. And let's change it to sudo while we're at it. Oh. What? Root. It switches it. Oh. Oh, okay. Yep. Okay. Because I have the, I'm using the tilde here, it's gonna, that's the home directory of the user that it's running as, which in the case of sudo is root, and so it's going to root. So we need to change this to slash, I don't even know. cd slash, isn't it? No, it's not user, it's home. There we go. Home Kevin dev. Yeah, okay. So it's going to be slash home Kevin dev. There we go. All right, let's save that. And now let's run it. I'm not sure what it's thinking about. Not sure why that is having a hard time. What happens if we just try to run that straight up? Oh, this is why it's stuck at this prompt. So continue, no. I wonder if there is a like help. And oh, sorry. To where like we can ignore that. Save original. Save, restore. Okay, so this might be a hang up. Like, how do we automatically answer a prompt that it's not showing us? We may need to... Once it's... So, sorry, let me run this again to show you what I'm thinking in my head. So the first time you run it, you get the rewriting EEPROM with new contents. And the reason it does this is because it doesn't have a baseline yet. And so if I were to say yes here, for example, and now if I run it again, I'm fairly certain it won't ask me that. It won't prompt me that again. So let's just try that. Yeah, no change from existing EEPROM contents. And honestly, I don't know where it's getting. It's not like there's a file or anything. I'll have to figure out a way to get around that. But let's go back to running our shell script. Okay, and you can see nothing came out of that because it didn't find anything. And what I have this for is EC. I feel like it's going to be a little easier to parse. It should say 0. And the reason the C says count how many lines you found. And so essentially what we're doing is I want to find the lines that match the settings here. And so I only halfway went through this. I need battery charge detect enabled to be true. Right now it's false, so it's not finding that line. And so there's 4 settings, I believe, 4 settings. And unless all 4 of them are set, history, then something's wrong. FTX prog. It is Oh. FTX prog. There we go. Okay, this is the line that we have to run. Might as well throw it in here. So we need BCD to be on. That's one setting. We need CBus 0 to be the BCD charger. We need CBus 1 to be power enable. We need the max bus power to be 500. And then CBus 2 and 3 to be tri-state. Again, remember, that's because by default, CBus 2 and 3 are active and doing things, which we want them to be tri-stated for low power reasons. So even though we only care about CBus 0 and 1 for our application, we need to remove these defaults from the factory of 2 and 3. And so there's 1, 2, 3, 4, 5, 6 lines that we need to validate. And so we need battery charge detect enabled to be true. We need maximum current supported from USB to be 500. So right here in the OR, this is going to be a really long line, but let's grab it from here. We want maximum supported current to be 500 milliamp. Then we need to put an OR in there. So again, we need the charger on, we need the current to be, and then we need the 4 C-bus lines. So let's start with C-bus 0 needs to equal what it was before, which I believe I have over here. Here we go. Let's see. Let's put this in. So C-bus 0 equals BCD charger, or C-bus 1 equals power enable, or C-bus 2 equals tri-state, and C-bus 3 equals tri-state as well. Okay. And again, I just want to recall back to something I said earlier. I had started writing a Node.js program to like child process exec this and then read the standard out, and that will work, but it's overkill because again, now if I want to run it in a container, now I need the entire Node.js environment installed. Whereas if I just use grep and the C++ FTX prog, those two things can give me the same information in what you can see here is, albeit a very long, but a single command line. And so I think that's everything. 1, 2, 3, 4, 5, 6. So it needs to see all of these things. And so the result of that should be a count of 6. And if the count is not 6, then something's wrong. And so let's all right. So now we're just going to go to the handy dandy. I'll even bring it over here. That variable from, I don't know, process return bash. How to return a value. So we could just say result equals that. What I really want is capture standard out of processing script. I want to capture that number, basically. No, this doesn't feel right. I only have a single line. Like, ugh. Somebody that's watching that's like a bash script expert's dying right now. No, that's the line by line that we just went to. Oh, okay. So it is. Just wrap it in the dollar. Okay, let's try it. Let's do. Oops, wrong one. Okay. So it sounds like we can do like, let's say count equals, and then just like wrap this whole thing. Is that true? And then do echo count. You can tell I'm a bash script writing expert. Let's run it and see what happens. Count, not found. Okay, so I know this is like killing you inside to watch, but this is the process I go through, so give me a break. Echo variable. Yeah. So I did do that, right? So yeah, okay. So I've got a mistake somewhere else is what's happening here. Oh, you know what? I bet these spaces are what are killing me. Let's try that. Aha! 0. Okay, and now just to test it, we can see that CBus 0 equals TXDN currently. So let's pick a different one. It's not as easy to, not as hard to change back. CBus 1, let's change this to be RX LED. And now that script should output 1 when we run it. And indeed it does. Cool. All right. So come back up here, undo that. All right. So this is how we're going to validate. So we can, I know you can create functions in bash scripts. I'll worry about that later for the interest of time. And what we'll do is say, what are we at on time? 47 minutes. All right, we're going to have to call it here soon. It's 2:18. Okay. So the first thing that we're going to want to do is this. And, well, if we're going to put all of this into a container, we won't have the full path here, but we're testing it out. We would put everything into a folder in the image so that when the container in Docker ran, it's obviously not going to look at home Kevin dev for what it needs. FTX prog. Okay. And so we're going to run this, which should do everything we need. The problem I think we're going to have is it's going to stop and ask us, it's going to prompt us again. Almost assured of it. Okay. But whatever, let's try it and see what happens. Oh, see, now it actually, oh, because I'm not piping it. So it's saying, do you want to rewrite the thing? And you can see here, it's like got our changes. Power enable, BCD charger. And then we're at 500 and we're at enabled true. And these other two things are tri-stated. So I'll have to figure out how to fill in the prompt. I'm going to say yes. And then it should run the count and our count should spit out 6. Perfect. Okay. And so, great. So in 2 lines, and again, we're going to have to massage this a little bit. We have programmed 2 bash script lines. We have programmed and validated that our FTDI chip is programmed correctly. And you saw how fast that was, especially if I can get rid of the prompt and auto fill that in. You're talking like 2 or 3 seconds. And so, cool. All right, I think I'm going to wrap this up because we're almost at an hour, and I like to keep these under an hour. We talked a lot about where we were. Next time we can get more into doing the work. The final thing I want to cover is I'm going to build my firmware here with IDF. And when it's done, it gives you this. You can run IDF flash, but to do that, you need to have the source code. And what I don't want to do, I think, at this point, is I don't want the source code to be a part of the Docker image. I don't even know that I want to mount the source code into the Docker image, because if we look at this command really quickly, it says, or you can run this, but the first thing that they suggest is you can run the ESP tool with a port and a baud, and you notice that the baud is half of what I would set it to, so we'll ignore that. And then it says before default reset, after hard reset, chip ESP32, write flash, flash mode, all this. This is what basically this command down here is doing. Flash size detect, flash frequency, 40 megahertz, and then it's giving us addresses and what to flash. So at address 1000, we're going to flash the bootloader.bin. At address 8000, we're going to flash the partition table.bin. At address D000, we're going to flash the OTA data initial.bin. And at address 10,000, we're going to flash our main application firmware. And then at address 370,000, we're going to flash our storage.bin, which is our spiffs image. So all of those things need to be flashed onto the chip. And this is how we can do that in a single command. And so what I think I would like to do, and this is down the road, I'm not going to do this now because I don't have time, but I would like to set up a GitHub action or some other CI. I'm just using GitHub action as an example, to say when you create a new release on GitHub. So I've checked in things. It's not just merging into main or doing a push to a branch. Like when I create a new release saying I am ready and confident that this point of this branch, the main branch, is ready for a new revision of firmware. So I'm going to create a release. I'll do that. At that time, you can have that trigger a GitHub action. But what I will do as part of the release is I will include from the build directory here, you can see we've got the bootloader directory and we have our bootloader.bin, and we have in our partition table, we've got partition table.bin. We have the OTA data initial bin. We have our stat feeder firmware bin, and we have our storage bin. Those 5 things. You don't need the source code or anything. If you have those 5 files and IDF, you could program an ESP32 with our code. And so what I think I would like to do is to have the creation of a release in GitHub Actions create a Docker image that is that release that I can pull on the Raspberry Pi machines, whether I tag it as latest or whatever, so that when it pulls down like that image, that Docker image, when I run the container, it has the exact version of all the files that I need for that version or that release of the binary to flash onto devices. And so I think I will use this long command in my script instead of using idf.py-p port flash, because I don't want to have the code on the device that is doing the programming. Again, thinking just very little things that we can do now. What if on my next run, I do 1,000 of these? We did 500 this time. The next run, we do 1,000, and I say, hey, listen, factory that's doing these, can I give you some instructions for flashing these so that they show up here already programmed and I don't have to do anything? At that point, it would be nice to say, all you need is a Raspberry Pi and this Docker image, run this command, and it's done. They don't need to have the source code, which again, for obvious reasons, you don't want to give your source code out to, even if you trust the party that's doing that, or even if I just contracted this out, I don't want to give the source code out. I consider it IP, and so by doing it this way, all I do is give out those binaries. And again, there's stuff you can do to inspect the binary. It's not bulletproof, but because I can hear people saying like, "Oh, people could still figure it out." I get it. It's just without needing the source code with these 5 files in IDF, and there's a Docker image for IDF. Anybody could program the device, and so that's the direction I think that we're headed. I need to keep fleshing out this script. What we'll do eventually is we'll take the script once I've got it to a spot where I'm like, hey, this is the script I want to use to program. Now let's build a Docker image based on the IDF specific version that I'm using, so that I can put this script in there. I can put the 5 binary files in there and call that a nice packaged way to program our devices. So that's it. I think we're going to cut it off there. We're under an hour. We went through a lot of stuff here. I'm going to keep working on the script. I think I will try my best to stream when I work on the Docker image and go through that. It has been probably close to 2 years since I've built a Docker image, and so I'm going to have to go through a learning curve there that might be painful to watch, but it's the process that we're going through, and that's what I'm trying to share. If you have any questions, feel free to reach out. I love when people email me, and I've had some of you say, hey, I'm experiencing similar issues, or you saved me some time. I was going to run into that, but now I won't because you ran into it. I'm happy to be the first person in there to make the mistakes so that you don't make them. But that's going to do it. Thanks so much for watching. I hope everybody has an amazing rest of their day, and we'll see you next time.